Chapter 5.7 is inverse trigonometric functions. So we'll do the inverse sine, inverse cosine, and inverse tangent problems and solve some problems using these inverse functions. So if you remember, we'll start with the inverse sine here. So if you remember that for a function to have an inverse function, it has to be 1 to 1. And what that means graphically is it has to pass the horizontal line test. So this means if we draw any horizontal line on the graph, then it can only intersect the curve at most once. So if we look at sine here, the graph for y equals sine of x, anywhere we put a horizontal line, it's technically going to intersect that graph at an infinite number of points. So that means it would not have an inverse function. So in order for sine to have an inverse function, we have to make it pass the horizontal line test. And what that means is we have to restrict the domain. And the agreed upon domain for which we restricted is negative pi over 2 to pi over 2. So for negative pi over 2, the sine function is right here. Positive pi over 2, it's right here. So what we're going to do is pretend like the sine function only exists from negative pi over 2 to positive pi over 2. So technically we could have picked any portion for the sine curve that would pass the horizontal line test. We could have picked from here to here, that would have also worked, but the agreed upon domain is negative pi over 2 to positive pi over 2. So what we're going to do is, in order to find the graph of the inverse function for sine, we do it just like we always do, and we reflect it over the line y equals x, and that'll give us the inverse function. So if we did this, this would give us this graph here on the right, the inverse sine function. And we notice that if we remember also, when we're finding an inverse function, the x and y coordinates completely flip-flop. So originally the y equals sine of x went from negative pi over 2 to pi over 2 on the x-axis. That means for the inverse function, it's going to be negative pi over 2 to pi over 2 on the y-axis. And the domain for sine inverse of x is negative 1 to positive 1, because that was the range of y equals sine of x. So the way that we write this for these inverse functions is y equals sine inverse of x. So the little negative 1 superscript represents the inverse function. That is not an exponent of negative 1. It just represents the inverse function. So like I mentioned, the domain here is negative 1 to 1, and the range is negative pi over 2 to positive pi over 2, because that's the restricted domain of sine of x. So for the definition here, for the relation between sine inverse and sine, if we have y equals sine inverse of x, that means sine of y equals x. So they're inverse functions, so essentially they cancel each other off. Okay, I made a little note down here, a really important distinction. Sine inverse of x does not equal the reciprocal of sine. So the one on the left is the inverse function, the one on the right is the reciprocal, which we know equals cosecant of x. So inverses and reciprocals are not the same thing. So what we're going to be doing is evaluating exact values of sine inverse of x. So the way we can do this is using that definition that's right up here. We can let theta equal sine inverse of x, whatever it happens to be, and then we can rewrite theta equals sine inverse as sine of theta equals x. And what we have to do is remember the restricted domain. The restricted domain is negative pi over 2 to pi over 2 for theta. And for now, we can use this little table that we have down here. We have the theta values in the row for the first row, and then sine evaluated at those theta values for the second row. Okay, so notice that it goes from negative pi over 2 to positive pi over 2 for the restricted domain. Let's do a couple examples here. So let's find the exact value of sine inverse of radical 2 over 2. Okay, so if we want to set this up the way that we just mentioned it, we would say theta equals sine inverse of radical 2 over 2. So essentially sine inverse is an angle. So what this means in terms of sine is that sine of theta equals radical 2 over 2. So we're still looking for theta here. So what this now means is sine of what? Sine of theta, sine of what equals radical 2 over 2 on the interval negative pi over 2 to pi over 2. Okay, and we are using that interval because that's the restricted domain of sine. So what we can do is, hopefully this is one that we actually know off the top of our head here. There's multiple ways you can do it without using the table right up here. You could think of it using the unit circle, and you'd be using the unit circle from negative pi over 2 to pi over 2, which would be quadrant 1 and quadrant 4. Okay, so but using this table for now, so it's radical 2 over 2, so we're seeing what value of theta gives us radical 2 over 2. So here's radical 2 over 2. The value of theta that gave us that was pi over 4. So that means theta equals pi over 4. And that also means that that's what our answer is. So sine inverse of radical 2 over 2 equals pi over 4. So obviously this is probably as easy as just looking at the table without having to write any of the other stuff that I wrote. But that's technically what's going on with these questions. Okay, next one we have sine inverse of 1/2. So once again, we can let theta equal this, which means sine of theta equals 1/2. And we're looking for theta here. So we're saying to ourselves, sine of what equals 1/2 when theta is between negative pi over 2 and positive pi over 2. So going up to this table, we're looking for 1/2. So we actually find it right here. And the angle that gives it to us is pi over 6. So our answer here is pi over 6. So sine inverse of 1/2 is pi over 6, and that's because sine of pi over 6 equals 1/2. Okay, so next for the cosine function. So this is obviously going to be really similar to the sine function one that we just did. So just like the sine function, cosine does not pass the horizontal line test, so we have to restrict the domain. We're going to restrict the domain of cosine from 0 to pi in order for it to have an inverse function. So this would be from, here it is at 0, and here it is at pi. So on the interval connecting those, that's going to be our restricted domain. And once again, we could have put it other places as long as it passes the horizontal line test. We could have done it from here to here. That would have worked, but the agreed upon domain is 0 to pi. And just like before, in order to get the inverse function of this, we're going to reflect that region that I shaded in. We're going to reflect that over the line y equals x. And if we do that, we're going to get this graph on the right. So notice that the range of this inverse function for cos inverse of x, it goes from 0 to pi. So that's the range because that was the restricted domain of cosine. And notice that the domain of cos inverse is -1 to 1 because that was the range of cosine. So once again, as always, inverse functions have flip-flopped domains and ranges. And here's the inverse function y equals cosine inverse of x. And the relationship, just like for sine, is if y equals cosine inverse of x, that means cosine of y equals x. Okay, and then also, really similar here, make sure that you know cosine inverse of x is not equal 1 over cosine x. We have the inverse on the left and the reciprocal on the right. The reciprocal we know is equal to secant of x, which is not the inverse. Okay, so finding exact values of cosine inverse, pretty much going to be the same thing that we just did. We're going to let theta equal cosine inverse of x. And then we're going to rewrite it as cosine of theta equals x, and we have to make sure that we're on the restricted domain. And we can just use this table to help us figure out what satisfies cosine of theta equals whatever x value is in the problem. So we have this table from 0 to pi because that's our restricted domain. So pretty much all we'll have to do here is look inside these values to see what theta value gives us that output value. Okay, first example, let's find the exact value of the following. We have cos inverse of negative radical 3 over 2. So we can set this up like this. Theta equals cosine inverse of negative radical 3 over 2. So what that means is that cosine of theta equals negative radical 3 over 2. So we should be saying to ourselves cosine of what equals negative radical 3 over 2 on the interval 0 to pi. And taking a look at this table, negative radical 3 over 2 is right here. So the angle that gives us that is 5 pi over 6. So that means that's our angle, which is our cosine inverse of negative radical 3 over 2. Okay, next one we have cos inverse of 1/2. So set this up the same way as we just did. So that means cosine of theta equals 1/2. So cosine of what equals 1/2 on the restricted domain. We can go up to this table. The one that gives us out a 1/2 is right here. That's going to be theta equals pi over 3. So that's going to be theta is pi over 3. So that means cosine inverse of 1/2 equals pi over 3. Okay, we'll do one that's a little bit trickier here. We have cosine inverse of 3 over 2. So starting the same way as before. So we get cosine of theta, after we let theta equal that, we get cosine of theta equals 3 over 2. So if we want to go look up here at the table, there's no 3 over 2 here, right, in this whole entire bottom row. So technically you could just be thinking, okay, well maybe it's just not included in that list. But what we should know before even looking at that table is we have to take into account the domain of cosine inverse and the range of cosine, because they're the same thing. Cosine of theta will never equal 3 over 2. The range of cosine is -1 to 1. 3 over 2 is 1.5. That is outside the domain of cosine inverse, outside the range of cosine. So what this means is that cos inverse of 3 over 2 does not exist. So that's the difficult part with these inverse ones. The domain is -1 to 1 so far for sine inverse and cosine inverse, so you have to take that into account. Also, if you could check these answers by plugging them in the calculator, make sure you're in radian mode, and it is the second button and it's behind sine, cosine, tangent. So you could type in, say, cosine inverse of 3 over 2, and it would tell you there's a domain error, so it would not work. Similarly, you could go back up here, type in cosine inverse of 1/2. It would give you your answer as a decimal. Pi over 3 is just a little bit over 1 if you divided them out. So it would give you that answer as a decimal, so that's how you can check your answer using the calculator. So for the inverse tangent function now, we have to restrict the domain for this one also for the same reasoning as the other two. So we restrict this domain to from negative pi over 2 to pi over 2. So that's going to be that domain right there, so just those two middle asymptotes. So we're going to pretend like the tangent function only exists between those two values, and we're going to reflect it over the line y equals x once again to get its inverse function. So the graph of tangent inverse, so y equals tan inverse of x, is going to look like this graph on the right. So we had vertical asymptotes for tangent at negative pi over 2 and pi over 2. That means there's horizontal asymptotes at negative pi over 2 and positive pi over 2 for its inverse function. And since the range of tangent was negative infinity to infinity over that domain, the domain of tangent inverse is also negative infinity to positive infinity. Okay, and the relationship between tan inverse and tangent, we have if y equals tan inverse of x, that means tangent of y equals x. And for the third time, inverse of tangent is not equal to the reciprocal of tangent. Okay, and now for finding the exact values, once again, super repetitive just like the other ones. If we're trying to evaluate tan inverse of x, we're going to let theta equal that. We're going to rewrite it as tangent of theta equals x, and we have to find what theta value makes that statement true, where theta is between negative pi over 2 and pi over 2 for that restricted domain. So for the theta values here, notice we're going from negative pi over 3 to pi over 3. We're not starting at negative pi over 2 and pi over 2 because that actually was not included in the restricted domain. That's why there was parentheses for interval notation. There was not brackets. Okay, but similar concept. We just have these main values between negative pi over 2 and pi over 2. So I'll just do two examples here for this one. So find the exact value of tan inverse of radical 3. So we let theta equal that, which means tangent of theta equals radical 3. So tangent of what equals radical 3? We go up here on the table and we see that radical 3 is right here for tangent. And the angle that got us there was pi over 3. So tan inverse of radical 3 equals pi over 3 because tangent of pi over 3 equals radical 3. Okay, let's do one more here for B. So we have tan inverse of negative 1. So setting this up with our theta, we let theta equal that, which means tangent of theta equals negative 1. So let's go back here to the graphs and actually think of this one a little bit differently. So if we go back up the tangent, on this interval here from negative pi over 2 to pi over 2, it's saying tangent of what equals negative 1. Well, here is negative 1 right here. So tangent equals negative 1 right here. So it's saying what value gives us that output. That would be whatever value is right here, whatever x value is right here. So it looks like it might be negative pi over 4 because it's halfway to negative pi over 2. So that's one way to think of it graphically. The other way is going to the inverse function, and it's saying tan inverse of negative 1, the question that we're still doing, tan inverse of negative 1. So here is negative 1. Now it is the x value. Tan inverse of negative 1. What does that equal? Well, that equals this right here, which once again looks like it's negative pi over 4 because it's halfway to negative pi over 2. So it's a completely opposite way of thinking about it when you're thinking about it in terms of tangent or thinking about it in terms of tan inverse. Okay, so if we go up to the table here, negative 1, tangent of theta is negative 1 right here. The theta value is actually negative pi over 4. So that would be our answer for that one. So tan inverse of negative 1 equals negative pi over 4. So the way I just we went over that graphically there with tangent and tan inverse, you can feel free to go back and look at the ones with sine of x and cosine of x, and you use their graphs to help you answer these questions also, or at least verify the answers. So now for the next thing, for composition functions, it's going to get a little bit harder. Questions will get a little bit longer. So if you remember, for inverse functions, the composition of inverse functions, which essentially means taking one function as the input to the other one. So if we do the function f of x and we plug in f inverse, and that equals x. That's the definition of inverse functions when that happens. So a lot of the times when we have these composition functions that we'll do in a second, they will cancel each other off, and all you're going to be left with is whatever that x value is. The secret here, the key to this, is it has to be in the domain of, in this case, f inverse. So for the second one here, if we do f inverse of f of x, that will cancel off to whatever the x is, only when x is in the domain of f of x. So that's probably pretty confusing for now, but I'll bring that up again once we start these problems. So when we're evaluating these composition functions, so I'll scroll down so you can see what they look like. So for example, sine inverse of sine theta. So when we're evaluating these, sometimes we can use that shortcut method that's written right above this by determining if the angle or the x value lies within that domain. If it does not lie in that domain, then we're going to evaluate the inside expression first. But we have to be a little careful, because if the inner function is the inverse function and x does not lie within the domain, then the value does not exist. So here's just a little kind of mini key for the domains and restricted domains of all of the functions that we work with. So we have the domain of sine x, cosine x, and tangent x, just the regular ones. So here are the regular domains that we're used to, and then on the right we have the restricted domain of each one also. Okay, so the only thing that's new here is the restricted domain on the right. And the bottom three, we have the inverse functions as well as their corresponding domains. So sine inverse and cosine inverse, the domain for those are -1 to 1. So we can only plug in values between -1 and 1. And for tangent inverse, the domain's -infinity to infinity. So that won't actually pose a problem at all because the domain's all real numbers. Okay, so let's actually do an example here to see what I mean for these. So sine inverse of sine of pi over 4. So what we could do here is we could always go to this middle one, this middle function, the inner function, and we can evaluate that expression. Sine of pi over 4, we would get a value. We would actually get radical 2 over 2. And then we could evaluate sine inverse of radical 2 over 2, which would give us pi over 4. The shortcut here is recognizing that pi over 4 is in the restricted domain. So what that means is that the inverse, sine inverse of sine of pi over 4, since pi over 4 was in the restricted domain of sine, that means the answer is just pi over 4. So whenever it happens like that, where it's in that domain or in that restricted domain of the inner function, the inverse function and the function itself just cancel each other out, and you're just left with whatever value that is. Okay, next one we have sine inverse of sine of 5 pi over 4. So we have an inverse of sine on the outside, sine on the inside. We have to be a little bit careful here because 5 pi over 4 is not in the restricted domain. So what this means is we cannot just cancel them out and say this is equal to 5 pi over 4. We're going to have to evaluate sine of 5 pi over 4 first. Okay, so we can actually do this using a reference angle. So 5 pi over 4 would be in quadrant 3. So here's the angle right here, 5 pi over 4. The reference angle would be right in here. And then we have to find that reference angle. The reference angle would be, hopefully we're good at this by now, the reference angle would be pi over 4. And then what we have to do is evaluate sine at the reference angle, which is radical 2 over 2. So for that, you can use that table that's on the sheet for us, the trig functions evaluated at the reference angles table. And now we have to figure out if sine of 5 pi over 4 is negative or positive based on what quadrant we're in. We're in quadrant 3, so we know that sine is negative in quadrant 3, so that means sine of 5 pi over 4 is negative radical 2 over 2. Okay, so that means we go all the way back up to the beginning here, all the way back up to the original question. And instead of sine inverse of 5 pi over 4, we just figured out that that was negative radical 2 over 2, so we plug that back in there. And now we can look this up on the table for sine. So just like from several questions ago, we would use that little table that was given to us, and we would see that this is equal to negative pi over 4. Okay, so sine inverse of sine of 5 pi over 4 equals negative pi over 4. So it wasn't as easy as the first one where they just cancel each other out. Next one, we have cosine inverse of cosine of 4 pi over 3. Okay, so first we recognize that it's cosine inverse of cosine, so we see if we can use our shortcut. So our shortcut here won't work because 4 pi over 3 is not in the restricted domain of cosine, which was the domain 0 to pi. So what we have to do is we have to evaluate cosine of 4 pi over 3 first. So 4 pi over 3 is in quadrant 3. I'm going to do this using the reference angle again. So this is going to be quadrant 3. This is our angle. Our reference angle is going to be right in here. So finding that reference angle, we would get a reference angle of pi over 3. And next we're going to evaluate cosine at that reference angle. So cosine of pi over 3, that equals 1/2. Once again, we have a table that we could use if we want to for that. And then we have to think, is cosine positive or negative in this quadrant? This is quadrant 3. Cosine is negative in quadrant 3. So that means the cosine of 4 pi over 3 equals negative 1/2. Okay, so we go back up here now and we are finding cosine inverse. Instead of cosine of 4 pi over 3, it's equal to negative 1/2, so we plug that in. So now we can use that table from this chapter once again, just like one of the questions from several pages ago. Cosine inverse of negative 1/2. We would see that that equals 2 pi over 3. So once again, that's from the table several pages ago, right here. So it was negative 1/2, theta equals 2 pi over 3. Okay, so that is the answer for that one. Okay, I'll do a couple more here. So we have cos inverse of cosine of 3 pi over 2. So 3 pi over 2 is not in the restricted domain for cosine, which was 0 to pi. So we can't just cancel these out and say that the answer is 3 pi over 2. So we have to evaluate cosine of 3 pi over 2. So this is actually one of the secretly easier ones. We have to remember that cosine of any value that is an odd integer multiple of pi over 2 will equal 0. So if we didn't remember that and we tried to come up with draw the reference angle for it, 3 pi over 2 would be the negative y-axis, so we wouldn't be able to do the reference angle method for this. So what's going to be the easiest way to remember this? You could always plug this in the calculator, I suppose, and it would give you the answer of 0, so it wouldn't give you a nasty decimal answer, so you could actually do it this way. Anytime your terminal ray is on one of these axes, think in terms of the unit circle. So on the unit circle, this would be cutting through the point 0, negative 1. And on the unit circle, cosine is equal to the x-coordinate. So that means cosine of 3 pi over 2 equals 0. Okay, so this was not the reference angle way, this was the unit circle way of thinking about it. Okay, so this means that going back to the original question, we are evaluating cos inverse of 0. So this one, going back up to that table from several pages ago, so this is saying that cosine of what equals 0 from 0 to pi. So here's the 0 right here, and the angle that got us that was pi over 2. So cos inverse of 0 equals pi over 2. So this whole thing, cos inverse of cosine of 3 pi over 2 just equals pi over 2. Okay, so I'll do like 3 or 4 more here. So tan inverse of cosine of pi. So this time we don't have the same trig function. We have tan inverse, then we have cosine. So no matter what here, we're going to have to evaluate cosine of pi. So cosine of pi, this one, hopefully we know what this equals. The unit circle and maybe the graphs should help you remember what this is going to equal. Cosine of theta, cosine of pi equals -1. So if you use the unit circle, that would be a flat angle or a straight angle. So it's cutting through the x-coordinate of -1, which is what cosine of theta equals on the unit circle. So that means this is going to be tan inverse of -1. And then once you have it set up this way, you can use that table from several pages ago. This is saying tangent of what equals -1 on the interval -pi over 2 to pi over 2. So scrolling back up to that table, we see tangent of theta equals -1 when theta is -pi over 4. So -pi over 4 is going to be our answer here. So for this one, since there was 2 different trig functions, it wasn't too difficult because cosine of pi was relatively easy to find, but you won't be able to use that shortcut method when there are 2 different ones. Okay, next we have cosine of tan inverse of 5 over 12. So this time we have the inverse function as the inner, the inverse expression as the inner expression here. So we would have to evaluate that first. We have different trig functions. We have cosine and tangent, so we can't use the shortcut method of possibly canceling each other out. So what we would try to do is we would try to evaluate this first. So we try to evaluate tan inverse of 5 over 12 first. So if we went to the table here, just like a question from several pages ago, 5 over 12 is not anywhere here, so we can't actually use this table method. So we're going to have to do this a different way. So what we're going to say is that we're going to let this whole thing equal theta. So we're going to say that theta equals tan inverse of 5 over 12. So pretty similar to what we did several pages ago. And this means that tangent of theta equals 5 over 12. So what we're going to do is actually we're going to try to create a right triangle in the correct quadrant for theta. And then we'll find cosine of that angle, and that will be our answer. Okay, so to figure out what quadrant we're in, it's a little bit difficult here. We have tangent of theta is 5 over 12. So this is positive. So that means its tangent is positive in quadrant 1 or quadrant 3. So we know we're in quadrant 1 or quadrant 3. The other piece of information that we need, though, is a little bit tricky to think of. we have to use the restricted domain of tangent. So we know the restricted domain of tangent is negative pi over 2 to pi over 2. This, even though it doesn't look like it, this is telling us the quadrants. Negative pi over 2 to pi over 2 are going to be quadrants 1 or quadrant 4. So hopefully quadrant 1 is obvious because an angle of pi over 2, 0 to pi over 2 is quadrant 1. 0 to negative pi over 2, negative means clockwise, so that would put us in quadrant 4. So the one that they have in common here is quadrant 1. So we're going to draw this in quadrant 1. And we're going to create a right triangle. So that was our whole goal. Now we're going to use the fact that tangent of theta is 5 over 12. Tangent is opposite over adjacent. So we label the sides. And then we also need to find the missing side using the Pythagorean theorem, which is going to give us 13. Okay, so now that we have this triangle, to answer our question, it's actually very easy. Now we are looking for cosine of theta, because we said tangent inverse of 5 over 12 equals theta. Now that we have this triangle drawn out, all we have to do is read off the adjacent over hypotenuse side, which is 12 over 13. So cosine of tan inverse of 5 over 12 is 12 over 13. So when you have it set up like this, where they are different trig functions with the inverse as the inner function, and so they can't cancel out, your goal is to create a triangle, and just you have to determine what quadrant it's in based on the restricted domain and whether or not the inverse function's input is positive or negative. Okay, so let's do 2 more for these ones, and then we'll move on to the last thing. So we have cotangent of sine inverse of negative 1/3. So once again, we recognize that these are not the same trig functions, so we can't possibly cancel them out. So what we have to do is evaluate the inner one first. So we're going to say theta equals sine inverse of negative 1/3. And what that means is sine of theta equals negative 1/3. So once you get to here, what you might want to do is check the table that we used in this section and see if it's on that table for negative 1/3, but it is not on the table, so we have to draw a triangle again. So we have to recognize that sine of theta is negative because it's negative 1/3. We know sine is negative in quadrants 3 and quadrant 4. And then we also have to use the fact about the restricted domain. The restricted domain for sine is negative pi over 2 to positive pi over 2. So that is also in quadrant 1 and 4, just like the last question. So the one that they have in common here is going to be quadrant 4. So we're going to create another right triangle, so it's going to be in quadrant 4 this time. Okay, so drawing our right triangle here, we get this. Filling in our sides. Sine of theta is negative 1/3. We know that sine is opposite over hypotenuse, so that's going to be 1 and 3. And this is in the negative y direction, so we know that that side had to be negative 1. So finding the missing side here, we would use Pythagorean theorem again. So we would have, I'll call that side A, so we'd have a squared plus negative 1 squared equals 3 squared. So solving this for a, we would end up getting the square root of 8. I'm going to simplify this. This simplifies to right here, 2 radical 2. So remember, if we're simplifying square roots like that, you think of 2 factors where one of them is a perfect square. 8 can be rewritten as 4 times 2. So the square root of 4 times 2 would be 2 radical 2. So we fill in that missing side. So once we have that set up, now it's nice and easy. All we have to do is evaluate cotangent of theta using that triangle. And cotangent is going to be the reciprocal of tangent. So it's adjacent over opposite, which is going to be 2 radical 2 over negative 1, which is just negative 2 radical 2. So that's cotangent of sine inverse of negative 1/3. Okay, and the last one here. We have secant of cos inverse 5/2. So for this one, you might be thinking, let's start it off the same way that we've been starting it off the past couple ones. Let's let that equal theta, and then create a right triangle. However, there is an issue here. 5/2 is not in the domain of cos inverse. So that's where it gets a little tricky. You should ask yourself every time before you start doing it, is it in the domain if it's one of the inverse ones? The domain of cosine inverse is from -1 to +1. 5/2 is not within those two numbers. That means this whole entire thing does not exist. So if that inside function is an inverse function and it's not in that domain, then it does not exist. You only have to worry about it when it's inverse sine or inverse cosine, because inverse tangent, the domain's -infinity to +infinity. Okay, so that one was pretty easy. Didn't have to do any work for it. It just had to say that it did not exist. So we'll do about 2 or 3 more pages of just some short questions here and then be done. So now we're going to be given a right triangle and we're going to solve for the angle given to the sides using these inverse properties. So for this first one, we want to solve for theta, and it's going to be in radians. So we have this right triangle, we have theta down here. We're given this side and this side. So if we are looking for theta, given the adjacent side and the hypotenuse side, it is in our best interest to use cosine. So cosine of theta equals adjacent over hypotenuse. Solving this for theta, that means theta equals cosine inverse of radical 2/2. So since this answer wants it in radians, we're going to want the exact answer, most likely using the table, or hopefully we start to have some of these memorized. So we think cosine of what angle equals radical 2/2? That would be pi/4. So our angle here in radians is pi/4. So in degrees, this would be 45 degrees. Next one, we have this triangle where we have theta up here this time, and we have the opposite side and the hypotenuse side. So if we're given opposite and hypotenuse, we should be using sine. So sine of theta equals opposite over hypotenuse. So this means that theta is going to equal sine inverse of 1/2. And once again, we want this in radians, so you don't just want to plug this in your calculator and get a decimal answer out. So we think to ourselves, sine of what angle equals 1/2 from -pi/2 to pi/2? That would be 30 degrees or pi/6 radians. Okay, and let's do some where we're using the calculator and we are looking for it in degrees. So once again, if you're going to use your calculator, just make sure that if you're trying to find degrees, you are in degree mode. So let's solve for theta from this first one, so round to the nearest degree if necessary. So we have this angle right here. We have the opposite side and we have the adjacent side. So if we have opposite and adjacent, we could use tangent. So tangent of theta equals 10 opposite over adjacent, 10 over 20. So that means theta equals tan inverse of 10 over 20. And I'll make a little note that we should use our calculator. So plugging this in degree mode, you hit the second button and then you hit tangent. That's going to be theta equals round to the nearest degree, 27 degrees. So tan inverse of 10 over 20 is 27 degrees. Next one, we have this triangle. We have the angle up here this time, and we have the adjacent side and the hypotenuse. So we have adjacent, we have hypotenuse, we could use cosine. So cosine of theta equals adjacent over hypotenuse, 30 over 50, which means theta equals cos inverse of 30 over 50. Type that into the calculator, and we should get 53 degrees. Okay, so hopefully those are relatively simple. So let's do a couple word problems here. So for this first one, we have a building is 50 feet high. At a distance away from the building, an observer notices that the angle of elevation to the top of the building is 41 degrees. And to the nearest foot, how far is the observer from the base of the building? Round to the nearest foot. So let's create a picture. So a building is 50 feet high. So here's my super great drawing of a building. And we know that it is 50 feet. So I'm going to leave out units actually. I'm just going to put 50. So we know that that's 50. And we have an observer. So we have somebody down here. And they're a certain distance horizontally away from the building. And they notice that if they looked up to the building from where they're standing, it creates an angle of 41 degrees. So this angle right here is 41 degrees. And they want to know how far is the observer from the base of the building. So we're going to be looking for this distance right here, which is our x. Okay, so our angle, and from our angle, so we also have a right triangle here, so obviously really important or we couldn't do this. So our angle here, we have the adjacent side and the hypotenuse side filled in. Or sorry, the adjacent side and the opposite side. So 50 is opposite, x is adjacent. So that means we're going to use tangent. So we're going to say tangent of our angle 41 degrees equals opposite over adjacent. We solve this for x. Essentially, all we have to do here is multiply. We're cross-multiplying. So we're going to multiply both sides by x, and then divide both sides by tangent of 41 degrees. So when we do that, we're going to get x times, I'll do it in 2 steps. So we cross-multiplied x over, and now we divide both sides by tangent 41 degrees. Once again, when you plug this in the calculator, make sure it is in degree mode. And we get 58 feet. Okay, it's good to kind of make sure your answer makes sense. 58 feet in terms of the other numbers in the problem seems relatively reasonable. Next one, find the shadow cast by a 10-foot lamp post when the angle of elevation of the sun is 58 degrees. Find the length of the nearest tenth of a foot. Okay, so we draw our lamp post. So that's a lamp post. And we have a shadow being cast, so there's a shadow on the ground. So there's the shadow. And we know the lamppost is 10 feet tall. And we have this angle of elevation from the end of the shadow, which is 58 degrees. So this angle is 58 degrees. So we create this right triangle. And we're looking for the length of the shadow. So we're looking for x right here. So once again, we're going to be using tangent. It's pretty much going to be the same setup. It's going to be tangent of 58 degrees equals opposite over adjacent. So we're going to multiply both sides by x and get x times tangent of 58 degrees equals 10. Divide both sides by the tangent number. We plug it in the calculator. We get x equals 6.2 feet when rounding it to the nearest tenth. Once again, seems pretty reasonable given these other numbers. Okay, last one here. A ladder leans against a brick wall. The foot of a ladder is 6 feet from the wall. The ladder reaches a height of 15 feet on the wall. Find to the nearest degree the angle the ladder makes with the wall. So we have drawing a picture, we have a wall. And we have a ladder leaning against the wall. So we have that super good ladder and that super good wall. So we can draw the ground going to the base of the ladder now. And we know that the ladder goes to a height of 15 feet on the wall. So the wall is going to be a height of 15. And the foot of the ladder is 6 feet from the wall. So that means right here is 6 feet. And we're looking for the angle the ladder makes with the wall. So we're looking for this angle right in here. Okay, so we have our right triangle here. So once again, this is actually going to be tangent. It's going to be tan theta equals opposite, which is 6 over 15, which is the adjacent. So solving this for theta this time, it's going to be theta equals tan inverse of 6 over 15. So we're going to have to plug this in the calculator when we're in degree mode, because we're going to want this in degrees. And we want the answer to the nearest degree. So plugging that in, we get 22 degrees is the angle. Okay, so that's it for this section. For these word problems, you just have to make sure you draw the picture accurately and then just use the same techniques that we were doing on the previous page. Okay, so that is it for 5.7.